This is the EdExcel A-Level Further Maths Paper 2 covering the Core Pure module, and this paper is from the June 2024 series. Question number 1, Part A. Use the definition of hyperbolic sin x in terms of exponentials to prove that 4 times hyperbolic sin x cubed plus 3 times hyperbolic sin x is equivalent to hyperbolic sin 3x. Let us focus on what we have on the left hand side, shown here. We can rewrite hyperbolic sin x in terms of exponentials, and in doing so we would have 4 multiplied by e to the x subtract e to the negative x over 2, which is what hyperbolic sin x is equal to, and then we cube this, and then we add on 3 times by e to the x subtract e to the negative x over 2. So we have 4 multiplied by e to the x subtract e to the negative x cubed, and then we divide this by 2 cubed, which is 8, and then we add on to this 3 times by e to the x subtract e to the negative x over 2, which is 3 times e to the x subtract e to the negative x over 2. And recognizing that 4 over 8 is 1/2, we would have e to the x subtract e to the negative x cubed over 2 plus 3 times e to the x subtract e to the negative x over 2. Now we can use the binomial expansion to work out e to the x subtract e to the negative x cubed. In doing so, we have 1 times e to the x cubed times e to the negative x to the 0 subtract 3 multiplied by e to the x squared multiplied by e to the negative x to the 1 plus 3 times e to the x to the 1 e to the negative x squared subtract 1 times e to the x to the 0 times e to the negative x cubed. And if we simplify this, we have e to the 3x subtract 3e to the x plus 3e to the negative x subtract e to the negative 3x. And so we can replace e to the x subtract e to the negative x cubed with this result shown here. So we have e to the 3x subtract 3e to the x plus 3e to the negative x subtract e to the negative 3x over 2, and then we add on to this 3 times e to the x subtract e to the negative x over 2. So we have 3e to the x subtract 3e to the negative x over 2. We have e to the 3x, and then we have negative 3e to the x plus 3e to the x, which simplifies to 0. Then we have 3e to the negative x subtract 3e to the negative x, which simplifies to 0, and then we have negative e to the negative 3x, and then we divide this by 2. Using the definitions of hyperbolic sine, e to the 3x subtract e to the negative 3x over 2 is hyperbolic sine of 3x, and that is indeed what we have on the right hand side. Part B. Hence, solve the equation hyperbolic sine 3x equals 19 times hyperbolic sine x, giving it answers as simplified natural logarithms where appropriate. We have the given equation as shown, and what we can do to begin with is rewrite the left hand side and the right hand side in terms of exponentials, and for that we would have to use the definitions of hyperbolic sine. On the left hand side we have hyperbolic sine 3x, which is e to the 3x subtract e to the negative 3x over 2, and on the right hand side we have 19 times hyperbolic sine x, which is 19 times by e to the x subtract e to the negative x over 2. If we multiply both the left hand side and the right hand side by 2, and then multiply the 19 into the bracket, we will be left with e to the 3x subtract e to the negative 3x equals 19e to the x subtract 19e to the negative x. If we rearrange, we would have e to the 3x subtract e to the negative 3x subtract 19e to the x plus 19e to the negative x equals 0. We will now multiply each term by e to the 3x. E to the 3x multiplied by e to the 3x, that is e to the 6x. Negative e to the negative 3x multiplied by e to the 3x, that's negative 1. Negative 19e to the x multiplied by e to the 3x, that's negative 19e to the 4x. 19e to the negative x multiplied by e to the 3x, that is 19e to the 2x. And so this is equal to 0. We can rewrite the exponentials in terms of e to the 2x. That is to say, we can rewrite the e to the 6x as e to the 2x cubed. Then we have the negative 19e to the 4x. We can rewrite that as negative 19 times e to the 2x squared. We then have 19 times e to the 2x, and then we have this negative 1, and this is equal to 0. What we have here is a hidden cubic. The way we can solve this is to let y equal e to the 2x. So we have y cubed, subtract 19y squared, plus 19y, subtract 1, equals 0. We now have to solve this cubic. If we go to the equation sub-menu, we have a polynomial of degree 3. We have y cubed, subtract 19y squared, plus 19y, subtract 1, equals 0. We've got this 17.94, etc. We've got this 0.055, etc. And we also have this 1. So we know that y equals 1 is a solution of this cubic, meaning y subtract 1 is a factor of this cubic. What we can now do is factorize this cubic because we know one of the linear factors. We have y times by y squared, which gives us y cubed. We have negative 1 multiplied by 1 gives us negative 1, and by inspection we have negative 18y. That is because we would have y times by 1 multiplied by negative 1 times by negative 18y, which gives us the 19y. So we have y subtract 1 multiplied by y squared subtract 18y plus 1 equals 0. We now need to solve for y. Well, if we have y subtract 1 equaling 0, that means y will equal 1. Now, we have to also solve y squared subtract 18y plus 1 equals 0. And we can do this using our calculator. We have a polynomial of degree 2. We have 1y squared subtract 18y plus 1 equals 0. So we have 9 plus 4 root 5 and 9 subtract 4 root 5 as our solutions. So we have as well y equals 9 plus minus 4 root 5. And as we said e to the 2x is what y is, that means e to the 2x is equal to 1 and 9 plus minus 4 root 5. If we take logs of both sides, 2x will equal the natural log of 1, the natural log of 9 plus 4 root 5, and the natural log of 9 subtract 4 root 5. The natural log of 1 is just 0, so 2x is equal to 0, the natural log of 9 plus 4 root 5, and the natural log of 9 subtract 4 root 5. We can now divide each of these by 2 to find out what x is. 0 divided by 2, that's just 0, and then we have a half times the natural log of 9 plus 4 root 5, and a half times the natural log of 9 subtract 4 root 5. So we've got this 0, and we can rewrite a half times the natural log of 9 plus 4 root 5 as a half times the natural log of 2 plus root 5 squared. And similarly, here we would have a half times the natural log of 2 subtract root 5 squared. And that's because 2 plus root 5 squared is 9 plus 4 root 5, and 2 subtract root 5 squared is 9 subtract 4 root 5. And if we use the power law of logs, we would have 2 times by the half, which is 1. So we have the natural log of 2 plus root 5 and the natural log of 2 subtract root 5. So x is equal to 0, the natural log of 2 plus root 5, and the natural log of 2 subtract root 5. Question number 2. F of x is equal to the inverse hyperbolic tan of 3 subtract x over 6 plus x, where the mod of x is less than 3 over 2. Part A. Show that f dash of x is equal to negative 1 over 2x plus 3. If we take a look at the formula book, in the differentiation section you can see the differential of the inverse hyperbolic tan of x is equal to 1 over 1 subtract x squared. So we have f of x, which is equal to the inverse hyperbolic tan of 3 subtract x over 6 plus x. And so f dash of x, that will equal 1 over 1 subtract 3 subtract x over 6 plus x squared, and using the chain rule we have to multiply by the derivative of 3 subtract x over 6 plus x. Now, if we think about the derivative of 3 subtract x over 6 plus x, we can work this out using the quotient rule. We have u, which is 3 subtract x, and v, which is 6 plus x. And so we have v, 6 plus x, times by u dash, negative 1, subtract u, 3 subtract x, times v dash, which is 1, divided by v, 6 plus x, squared. So we have negative 6, subtract x, subtract 3, plus x, divided by 6 plus x squared. And this is equal to negative 9 over 6 plus x squared. And so f dash of x will equal 1 over 1 subtract 3 subtract x over 6 plus x squared multiplied by the derivative of 3 subtract x over 6 plus x, which we worked out to be negative 9 over 6 plus x squared. So we have 1 over 1 subtract. Now here we would have 3 subtract x squared over 6 plus x squared. and then we multiply by negative 9 over 6 plus x squared. So we have 1 over 1 multiplied by 6 plus x squared over 6 plus x squared, subtract 3, subtract x squared over 6 plus x squared, times negative 9 over 6 plus x squared. You can see here we've got this common denominator of 6 plus x squared. So we have 1 over this common denominator of 6 plus x squared is shown here, and then we have 6 plus x squared subtract 3 subtract x squared, and we multiply this by negative 9 over 6 plus x squared. The 6 plus x squared and this 6 plus x squared simplify to 1. We've got 1 multiplied by negative 9, and so we end up with negative 9 over 6 plus x squared subtract 3 subtract x squared. You'll notice for the denominator we have a difference of 2 squares, so we have negative 9 over 6 plus x plus 3 subtract x multiplied by 6 plus x subtract 3 subtract x. So we've got negative 9 over, now here, 6 plus x plus 3 subtract x is 9, and 6 plus x subtract 3 subtract x, that's 2x plus 3. So we've got negative 9 over 9 times 2x plus 3. And this simplifies to negative 1 over 2x plus 3, which is what we wanted to show. Part B. Hence determine f double dash of x. So, we've got negative 1 over 2x plus 3, which we can rewrite as negative 2x plus 3 to the negative 1. And so if we were to work out f double dash of x using the chain rule, this will equal negative 1 multiplied by 2x plus 3 to the power of negative 2 multiplied by the derivative of the bracket, which is 2. And this will simplify then to 2 over 2x plus 3 squared. Part C. Hence show that the Maclaurin series for f of x up to and including the term in x squared is natural log p plus qx plus rx squared, where p, q and r are constants to be determined. Here is the formula for the Maclaurin series. F of x is equal to f of 0 plus x times f dash of 0 plus x squared over 2 factorial times f double dash of 0. And we have higher order terms, but we are only interested in terms up to and including x squared. And here is that formula stated. So to begin with, we need to work out f of 0. We know what f of x is, that is inverse hyperbolic tan of 3 subtract x over 6 plus x equal inverse hyperbolic tan of 3 subtract 0 over 6 plus 0. And then we add on x times by f dash of 0. We worked out in part A what f dash of x is, that's negative 1 over 2x plus 3. Therefore, f dash of 0 will equal negative 1 over 2 times 0 plus 3. And then we add on x over 2 factorial, that is x squared over 2, multiplied by f double dash of 0. here is f double dash of x, that's 2 over 2x plus 3 squared. So f double dash of 0 is equal to 2 over 2 times 0 plus 3 squared. The inverse hyperbolic tan of 3 subtract 0 over 6 plus 0, well, 3 over 6 is a half, so we have inverse hyperbolic tan of a half, and here we have x multiplied by negative 1 over 3, so that's negative x over 3, and then here we end up with x squared over 9. The inverse hyperbolic tan of 0.5, that can be determined using the formula a half times the natural log of 1 plus x over 1 subtract x. So we have a half times the natural log of 1 plus 0.5 over 1 subtract 0.5, and then we have negative x over 3 plus x squared over 9. 1 plus a half over 1 subtract a half, that is 3. So we've got a half times the natural log of 3, subtract x over 3 plus x squared over 9. We can rewrite a half times the natural log of 3 as the natural log of 3 to the power of 1 half, and then we've got negative x over 3 plus x squared over 9, and 3 to the half is root 3, so we have the natural log of root 3 subtract x over 3 plus x squared over 9. Question number 3, part A. We have to explain why the integral of 1 over 9x squared plus 16 with respect to x with limits from 4 over 3 to infinity is an improper integral. Quite simply, the upper limit is infinite, and that's what we see here. Hence, we have an improper integral. Part B. Show that the integral of 1 over 9x squared plus 16 with respect to x between 4 over 3 and infinity is equal to k pi, where k is a constant to be determined. Before we do anything else, let's think about this integral of 1 over 9x squared plus 16 with respect to x. If we think about our standard integrals, we have this 1 over a squared plus x squared, which integrates to 1 over a times the inverse tan of x over a. So we need to somehow adjust this so it's of this form, 1 over a squared plus x squared. Now, we've got this 1 which we'll leave alone, and for the denominator I'm going to factorise out a 16. So I've got 16 multiplied by 9x squared over 16 plus 1. So I've got the integral of 1 over 16. Now let's think about this 9x squared over 16 plus 1. The 9x squared over 16, that is the same as 3x over 4 squared, and then we add on this 1. So let's take out a 1 over 16 outside of the integral, and then we've got 1 over 3x over 4 squared plus 1, which I'm going to rewrite as 1 squared. Now, what we have here is almost of this form here, but instead of us having an x, we've got a 3x over 4. And so therefore what we can do is make a substitution. We will let u equal 3x over 4, and in doing so we can find out what du over dx is. That's equal to 3/4, meaning dx is equal to 4 over 3 du. And so we've got 1 over 16 times the integral of 1 over u squared plus 1 squared multiplied by dx, which we've said is 4 over 3 du. 1 over 16 times 4 over 3, that's 1 over 12. So I've got 1 over 12 times the integral of 1 over u squared plus 1 squared with respect to u, which is now in an integrable form as we see here. Instead of us having an x, we've got a u, and instead of us having an a, we've got instead 1. Meaning we end up with 1 over 12 times the arctan of u plus c as our result. And because we know u is equal to 3x over 4, we have 1 over 12 times the arctan of 3x over 4 plus c. So the integral of 1 over 9x squared plus 16 with respect to x from 4 over 3 to infinity, that will equal, well, if we use what we have here, we have a 12 times the inverse tan of 3x over 4. Now because we've got an improper integral, we need to take the limit as t tends towards infinity, and the lower limit will stay the same as 4 over 3, but the upper limit now will change to t. So we've got 1 over 12 multiplied by, now if I substitute in for my upper limit, we've got the limit as t tends towards infinity of the inverse tan of 3t over 4, subtract, and if I substitute in 4 over 3 for my lower limit, we've got the inverse tan of 3 over 4 times 4 over 3. So I've got this 1 over 12. Now, as t gets very, very, very big, in other words, we go to infinity, the inverse tan of infinity essentially will be pi over 2. You can think of this to be where the asymptote is. And the inverse tan of 3/4 times 4 over 3, well here this is the inverse tan of 1, which is just pi over 4. So I've got a 12 times by pi over 2 take away pi over 4, that will equal pi over 48. Question number 4. Use the method of differences to show that the sum of 2 over r plus 4 times r plus 6 from r equals 1 to r equals n is equal to n times by an plus b over 30 times n plus 5 times n plus 6, where a and b are integers to be determined. Let us begin by focusing on this 2 over r plus 4 times r plus 6. We can rewrite this using partial fractions. We would have a over r plus 4 plus b over r plus 6, and we need to determine a and b. If we multiply through by r plus 4 times r plus 6, on the left hand side we have 2, and on the right hand side we have a times by r plus 6 plus b times by r plus 4. So, to find out what a and b are, we can choose values of r to help us find out what a and b are. Now if I choose r equals -4, this term will disappear, leaving us with 2 equals 2a, and therefore a is equal to 1. And if I choose r equals -6, this term disappears, leaving us with 2 equals -2b, meaning b is -1. We know what a is, we know what b is, and therefore 2 over r plus 4 times r plus 6, that will equal 1 over r plus 4 subtract 1 over r plus 6. Now, we've got this sum from r equals 1 to r equals n of 2 over r plus 4 times r plus 6. What this is the same as, using this result, is the sum of 1 over r plus 4 subtract 1 over r plus 6 from r equals 1 to r equals n. And now we need to substitute in terms from r equals 1 to r equals n and add those together. When r is equal to 1, I've got 1 over 1 plus 4, which is a fifth, subtract 1 over 1 plus 6, which is a seventh. When I substitute in r equals 2, I've got 1 over 2 plus 4, which is a sixth, subtract 1 over 2 plus 6, which is an eighth. When I substitute in r equals 3, I've got 1 over 3 plus 4, which is a seventh, subtract 1 over 3 plus 6, which is a ninth. When I substitute in r equals 4, I've got 1 over 4 plus 4, which is an eighth, subtract 1 over 4 plus 6, which is a tenth. Now we can continue on. We now need to work out the n-1th term and then the nth term. When I substitute in r equals n-1, I've got 1 over n-1 plus 4, that's 1 over n plus 3. And then I've got -1 over n-1 plus 6, which will be -1 over n plus 5. And then the nth term is when we replace the r with n. So I've got 1 over n plus 4 subtract 1 over n plus 6. And that's what we see here. We now have to see which terms cancel out. We've got this -1/7 cancelling with this 1/7. We've got this -1/8 cancelling with this 1/8. Now, if we think about what the -1/9 will cancel with, that will cancel with the 1 over n plus 3. And if I think about then what this -1/10 cancels with, that will cancel with the 1 over n plus 4. So in terms of what's left, we'd have this 1/5, this 1/6, this -1 over n plus 5, and this -1 over n plus 6. So we've got a fifth plus a sixth, subtract 1 over n plus 5, subtract 1 over n plus 6. And our job is now to simplify all this. A fifth plus a sixth, that's 11 over 30. Then we've got -1 over n plus 5 and -1 over n plus 6. What we have is a common denominator of 30 times n plus 5 times n plus 6. And so this term we can rewrite as 11 times by n plus 5 times n plus 6. This term we can rewrite as negative 1 times 30 times n plus 6. And this term we can rewrite as negative 1 times 30 times n plus 5. 11 times n plus 5 times n plus 6 over 30 times n plus 5 times n plus 6 will give me the 11 over 30. Negative 1 times 30 times n plus 6 over 30 times n plus 5 times n plus 6 will give me negative 1 over n plus 5. And negative 1 times 30 times n plus 5 over 30 times n plus 5 times n plus 6 will give me negative 1 over n plus 6. So let's continue working this out. Well, I've got this 11 multiplied by n plus 5 times n plus 6, so that's n squared plus 11n plus 30, and then I've got negative 30 times n, and then I've got negative 30 times by 6, and then I've got negative 30 times n, then I've got negative 30 times by 5, and I divide this by 30 times n plus 5 times n plus 6. Let's now multiply the 11 into this bracket, so I've got 11n squared plus 121n plus 330, and then we've got these terms here, negative 30n, subtract 180, subtract 30n, subtract 150. And we divide this by 30 times n plus 5 times n plus 6. Now for the numerator that will simplify to 11n squared plus 61n, and for the denominator that remains the same as 30 times n plus 5 times n plus 6. From the numerator we can factorize out an n. We would have n multiplied by 11n plus 61, and for the denominator we have 30 times n plus 5 times n plus 6. So we have a which is 11, b which is equal to 61. Question number 5. The locus C is given by mod of z subtract 4 equals 4. The locus D is given by the argument of z is equal to pi over 3. Part A. Sketch on the same Argand diagram the locus C and the locus D. If we think about the locus C, where we have the mod of z subtract 4 equals 4, we can rewrite this in Cartesian form. In Cartesian form, this is x subtract 4 squared plus y squared equals 4 squared. And if we think about this locus of D, where we've got the argument of z equaling pi over 3, that will be a half line with equation y equals x times by tan of pi over 3. And that is shown on the Argand diagram here. And you'll find for D we've rewritten that as y equals root 3x, and that's because the tan of pi over 3 is equal to root 3. We've called this Cartesian equation y equals root 3x equation 1, and this equation x subtract 4 squared plus y squared equals 16 equation 2, and of course 4 squared is 16. The set of points A is defined by A equals the set of complex numbers where the mod of z subtract 4 is less than or equal to 4, and the set of complex numbers where the argument of z is greater than or equal to 0 but less than or equal to pi over 3. Part B. Show by shading on your Argand diagram the set of points of A. For part B, we have the region shown shaded here. Part C. Find the area of the region defined by A, giving your answer in the form p pi plus q root 3, where p and q are constants to be determined. To find out this area, we need to recognize the following. We've got this triangle here, and we've also got this segment shown in blue here. The way we can find the green area is to work out the area of the semicircle. Then from that we can subtract this segment, and to find this segment we need to find the area of the sector and subtract from it the area of this triangle. What we will do to begin with is find out the point of intersection. We can find that point of intersection by substituting in equation 1 into equation 2. So we replace the y with root 3x. So we've got x subtract 4 squared plus root 3x squared equals 16. So I've got x squared subtract 8x plus 16 plus 3x squared equals 16. And so we would have 4x squared subtract 8x equals 0. So we have 4x times by x subtract 2 equals 0, meaning x is equal to 2. Now that we know x is equal to 2, we can sub this back into equation 1 to find out what the corresponding y is. And that will be 2 root 3. So the point of intersection between the line and the circle is 2 root 3. Now the radius of this circle is also the length of one of the sides of the triangle, and that is 4, because we are going from the origin to the point 4, 0. So let's find out the area of the semicircle to begin with. For the semicircle, we have a half times pi times 4 squared, which is 8 pi. Let us now find the area of this sector. We know that this angle here is pi over 3, or 60 degrees. Here we've got a x coordinate of 2, which is half of 4. We have an equilateral triangle. This is 4. This is also 4. And the angle is pi over 3. So we can find out the area of the sector. The area of the sector is a half times 4 squared times pi over 3, which is 8 pi over 3. We can now find out the area of the triangle using a half AB sine C. The triangle has an area a half times 4 squared times the sine of pi over 3, which is equal to 4 root 3. And so the segment will be the area of the sector take away the area of the triangle. So the area of the segment is 8 pi over 3 subtract 4 root 3. And so the area of A will be the area of the semicircle, 8 pi, subtract the area of the segment, which is 8 pi over 3 subtract 4 root 3. So the area of A then is equal to 16 pi over 3 subtract 4 root 3. Question number 6. The motion of a particle P along the x-axis is modelled by the differential equation 2 times by d squared x over dt squared plus 5 times dx over dt plus 2x equals 4t plus 12, where p is x meters from the origin O at time t seconds and t is greater than or equal to 0. Part A. Determine the general solution of the differential equation. Our first step is to state what the auxiliary equation is, and for that we have 2m squared plus 5m plus 2, and this is equal to 0. If I factorise, we would have 2m plus 1 multiplied by m plus 2 equals 0, meaning m equals negative 1/2 and m is equal to negative 2. So for the complementary function, xc, that's equal to some constant a multiplied by e to the negative t over 2 plus some constant b multiplied by e to the negative 2t. Because we have a non-homogeneous second order differential equation, on the right hand side you see we have a linear function 4t plus 12. And so for our particular integral we need to write that in a linear format. So we will try x equals pt plus q. If I differentiate this, dx over dt, that's equal to p, and d squared x over dt squared, that's equal to 0. We know what the second derivative of x is, we know what the first derivative of x is, and we know what x is. We can substitute these back into the differential equation. So we have 2 times by the second derivative 0, plus 5 times by the first derivative p, plus 2 times by the function x, so that's 2 times pt plus q, and this is equal to, well, on the right hand side we have 4t plus 12. So we can simplify this to 5p plus 2pt plus 2q equals 4t plus 12. For us to find out what p and q are, we can compare coefficients. So let's look at the t terms. On the left hand side I've got 2p of them, and on the right hand side I've got 4 of them. 2p is equal to 4, meaning p is equal to 2. Let's now look at the numbers. On the left hand side I've got 5p plus 2q, and on the right hand side I've got 12. I know what p is, that's 2, so I've got 5 times 2 plus 2q equals 12, meaning q equals 1. So we can replace the p with 2, we can replace the q with 1, meaning the particular integral is equal to 2t plus 1. And for our general solution, that is the sum of the complementary function plus the particular integral. Here is the complementary function, that's a e to the negative t over 2 plus b e to the negative 2, and we add on to this the particular integral 2t plus 1. Hence, this is our general solution. Part B. Hence determine the particular solution for which x equals 3 and dx over dt equals negative 2 when t equals 0. For part B, our first step would be to differentiate the general solution. We can find out what dx over dt is. If I differentiate the ae to the negative t over 2, we end up with negative 1/2 ae to the negative t over 2. If I differentiate be to the negative 2, we end up with negative 2b e to the negative 2t. If I differentiate the 2t, we end up with 2, and differentiating 1, we end up with 0. We know when t equals 0, x equals 3, so let's substitute back into the general solution. We have 3 equals ae to the 0 plus be to the 0 plus 1, and because e to the 0 is just 1, we have a plus b equaling 2, and that's because 3 subtract 1 is 2. We also know that when t equals 0, x dash is equal to negative 2. We substitute that back into here, so we have negative 2 equals negative 1/2 ae to the 0, subtract 2b e to the 0 plus 2, And because e to the 0 is 1, if we rearrange this equation, we end up with a plus 4b equals 8. And so if we solve a plus b equals 2 and a plus 4b equals 8 simultaneously, you will find a to equal 0 and b to equal 2. Now that we know what a and b are, we can use this to state our particular solution. We replace the a with 0, we replace the b with 2, meaning the particular solution is equal to 2e to the negative 2t plus 2t plus 1. Part C. For the first part, we have to show that according to the model, the minimum distance between O and P is 2 plus natural log 2 meters. For the first part of Part C, for us to find the minimum value of t, we first have to differentiate. So we need to differentiate 2e to the negative 2t plus 2t plus 1. So dx over dt will then equal negative 4e to the negative 2t plus 2. And now we set this equal to 0, so we've got 0 equals negative 4e to the negative 2t plus 2. So we have e to the negative 2t equals 1/2. If I take logs of both sides, we have negative 2t equals the natural log of 1/2. And if I divide both sides by negative 2, t will equal negative 1/2 times the natural log of 1/2, which we can rewrite as 1/2 times the natural log of 1/2 to the negative 1. 1/2 to the negative 1 is 2, so we have 1/2 times the natural log of 2, which is what the value of t is. Now that we know what the value of t is, we can substitute this back into x. So we need to substitute in back into here. So we've got x equals 2e to the negative 2 times 0.5 times natural log of 2 plus 2 times 0.5 times natural log 2 plus 1. So I've got 2e to the negative natural log 2 plus natural log 2 plus 1. We can now power slide this negative, so I've got 2e to the natural log 2 to the negative 1 plus natural log 2 plus 1. So 2 times e to the natural log of 2 to the negative 1, that's just 2 times 2 to the negative 1. Then we add on natural log 2, then we add on this 1. So we've got 2 times by 2 to the negative 1, that's just 1. We add on to this natural log 2, and then we add on to this 1. 1 plus 1 is 2, so I've got 2 plus natural log 2, which is what we wanted to show. For the next part, we have to justify that this distance is a minimum. For this, we have to find the second derivative of x. So we need to differentiate negative 4e to the negative 2t plus 2. And that's equal to 8e to the negative 2t. Now this will always be greater than 0, and that's just because of how the graph looks like. And so therefore, because the second derivative is greater than 0, here we have a minimum. For large values of t, the particle is expected to move with constant speed. Part E. Comment on the suitability of the model in light of this information. Because we are considered speed, we have to consider the first derivative of x with respect to t. And we know that's equal to negative 4e to the negative 2t plus 2. And we are concerned with what happens when t gets very large. Now, as t gets very large, e to the negative 2t tends towards 0. So this term tends towards 0, and then we are left with plus 2. So we have dx over dt tending towards 2. And because this is just a number, it's a constant, that means the particle moves with constant speed, and so therefore the model is suitable. Question number 7, part A. Determine the roots of the equation z to the 6 equals 1, giving your answer in the form e to the I theta, where theta is in between 0 and 2 pi. If we take a look in the formula book, you will note that the roots of z to the n equals 1 are given by z equals e to the 2 pi ki over n for k equaling 0, 1, 2, etc. up to n minus 1. So if we have z to the 6 equaling 1, z will equal e to the 2 pi ki over 6, which is the same as z equals e to the pi ki over 3. 2 over 6 is 1 over 3. The values of k we have for this would be 0, 1, 2, 3, 4, 5. Part B. Show the roots of the equation in Part A on a single Argand diagram. We see those 6 roots here. We've got e to the pi ki over 3 with different values of k from 0 all the way up to 5. Part C. Show that root 3 plus I to the 6 is equal to negative 64. We have this root 3 plus I, which we can write in mod arg form. If we go to the calculate submenu, let's change the complex mode to the third option where we have r theta. We have root 3 plus I, which you can see is 2, and then the argument is pi over 6, which means root 3 plus I is equal to 2e to the I pi over 6. And so now, when we deal with root 3 plus I to the 6, this is the same as raising 2e to the I pi over 6 to the 6th power. So what we have here is 2 to the power of 6 multiplied by e to the I pi, and that's because I pi over 6 times by 6 is just I pi. 2 to the 6, that's 64, and e to the I pi, that's negative 1. So we have 64 times negative 1, which is negative 64. Part D. Hence or otherwise solve the equation z to the 6 plus 64 equals 0, giving your answers in the form r e to the I theta, where theta is in between 0 and 2 pi. So for part D we have z to the 6 plus 64 equals 0, meaning z to the 6 is equal to negative 64. And recognizing that minus 1 is the same as e to the I pi, what this is equal to then is 64 e to the I pi. Equivalently, this is the same as 64 times cos pi plus I sin pi. Now we know that sine and cos are periodic. They repeat multiples of 2 pi. So we can rewrite this as 64 times cos of pi plus 2k pi plus I sine of pi plus 2k pi. This is what z to the 6 is, and so z will equal 64 times cos of pi plus 2k pi plus I sine of pi plus 2k pi to the 1/6, which is the same as 64 to the 1/6 multiplied by cos of pi plus 2k pi plus I sine of pi plus 2k pi to the 6th. 64 to the 1/6, that's equal to 2. And for the bit in the bracket, we can use De Moivre's theorem. So we have cos of pi plus 2k pi over 6 plus I sine of pi plus 2k pi over 6. And equivalently in exponential form, we have 2e to the pi plus 2k pi over 6 I, where k will equal 0, 1, 2, 3, 4, and 5. Question number 8. We are given the matrix A, and this is equal to 3, 1, negative 1, 1, 1, 1, k, 3, 6, where k doesn't equal 0. Part A, we have to find in terms of k the inverse of matrix A. The first thing we have to do is consider the sign convention. We will use this throughout the question. We have plus minus plus, minus plus minus, plus minus plus. The first step is to find the determinant of A. The determinant of A is shown here. If I expand along the first row, we have positive 3 multiplied by, well, I cover this row, I cover this column, and I take the determinant of what's left over, 1, 1, 3, 6. Then I have minus 1 multiplied by the determinant of, well, I cover the first row and the second column, and I've got what's left over, 1, 1, k, 6. And then I've got plus negative 1 times the determinant of, well, I cover the first row and the third column, and what's left over is 1, 1, k, 3. So I've got 3 times by, well, here I've got 1 times by 6, subtract 1 times by 3. Then I've got negative 1 times by 1 times by 6, subtract 1 times by k. And then I've got negative 1 times by 1 times by 3, subtract 1 times by k. So I've got 3 multiplied by 3, subtract 1 multiplied by 6, subtract k, subtract 1 multiplied by 3, subtract k. So I've got 9, subtract 6, plus k, subtract 3, plus k, which is 2k. The next step is to find the matrix of the minus. Now, for the first one, we have to cover up the first row and the first column and take the determinant of what's left over. So we have the determinant of 1, 1, 3, 6. For the next element, we cover up the first row and the second column, and we take the determinant of what's left over. So we have the determinant of 1, 1, k, 6. For the next element, we cover the first row and the third column, and take the determinant of what's left over. So we have the determinant of 1, 1, k3. For the next element, we cover the second row and the first column and take the determinant of what's left over. So we have the determinant of 1, negative 1, 3, 6. For the next element, we cover the second row and the second column and take the determinant of what's left over. So we have the determinant of 3, negative 1, k6. For the next element, we cover the second row and the third column and take the determinant of what's left over. So we have the determinant of 3, 1, k3. For the next element, we cover the third row and the first column and take the determinant of what's left over. So we have the determinant of 1, negative 1, 1, 1. For the next element, we cover the third row and the second column and take the determinant of what's left over. So we have the determinant of 3, negative 1, 1, 1. For the next element, we cover the third row and third column and take the determinant of what's left over. So we have the determinant of 3, 1, 1, 1. So we've got here 1 times by 6 subtract 1 times by 3. Here we've got 1 times by 6 subtract 1 times by k. Here we've got 1 times by 3 subtract 1 times by k. Here we've got 1 times by 6 subtract negative 1 times by 3. Here we've got 3 times by 6 subtract negative 1 times by k. Here we've got 3 times by 3 subtract 1 times by k. Here we've got 1 times by 1 subtract negative 1 times by 1. Here we've got 3 times by 1 subtract negative 1 times by 1. Here we've got 3 times by 1 subtract 1 times by 1. So we have 3, 6 subtract k, 3 subtract k, 9, 18 plus k, 9 subtract k, 2, 4, 2. Our next step is to find the matrix of the cofactors. So we've got this matrix, and then we apply this sign convention. So we apply the plus minus plus minus plus minus plus minus plus. So we have 3 k subtract 6, 3 subtract k, negative 9, 18 plus k, k subtract 9, 2, negative 4, 2. Our next step is to transpose this. What that means is we need to swap the rows and columns. So the first column would become our first row. So we have 3, negative 9, 2. The second column would become our second row. So we've got k subtract 6, 18 plus k, negative 4. And the third column would become our third row. So we have 3 subtract k, k subtract 9, 2. And so the inverse of A is equal to 1 over the determinant, so that's 1 over 2k, multiplied by this matrix shown here. Hence, what we see here is the inverse of A. Part B. Determine in simplest form in terms of k the coordinates of the point where the following planes intersect. 3x plus y subtract z equals 3, x plus y plus z equals 1, kx plus 3y plus 6z equals 6. What you will find is the coefficients of x, y and z for the system of equations shown here is what the matrix A is. So we can rewrite this system of equations in matrix form. We have the following. We've got this matrix 3, 1, negative 1, 1, 1, 1, k, 3, 6 times x, y, z equals 3, 1, 6. So we've got the matrix A times x, y, z equals 3, 1, 6, and we need to find out what x, y, z is. And we can do that by recognizing x, y, z is equal to A inverse times by 3, 1, 6. And we know what A inverse is, we work that out in part A. So we've got A inverse, which is 1 over 2k times 3, negative 9, 2, k subtract 6, 18 plus k, negative 4, 3 subtract k, k subtract 9, 2, multiplied by 3, 1, 6. So I've got this 1 over 2k, and then I've got the 3 times by the 3, then I've got the 1 times by the negative 9, and the 6 times by the 2. Then I've got 3 times by k subtract 6, plus 1 times by 18 plus k, plus 6 times by negative 4. And then I've got 3 times by 3 subtract k, plus 1 times by k subtract 9, plus 6 multiplied by 2. So I've got 1 over 2k times by, well, here I would have 9 subtract 9 plus 12. Here I would have 3k subtract 18 plus 18 plus k subtract 24, and 9 subtract 3k plus k subtract 9 plus 12. So I've got 1 over 2k times by 12, 4k subtract 24, 12 subtract 2k. And we can multiply each of these by 1/2, and we leave the 1 over k on the outside, so we would have 6, 2k subtract 12, 6 subtract k. As coordinates we have 6 over k, 2k subtract 12 over k, 6 subtract k over k. Question number 9. Figure 1 shows the central vertical cross-section ABCDEFA of a vase together with measurements that have been taken from the vase. The horizontal cross-section between AB and FC is a circle with diameter 4 centimeters. And if that's the case, then the radius will be 2 centimeters. The base of the vase ED is horizontal, and the point E is vertically below F, and the point D is vertically below C. Using these measurements, the curve CD is modelled by the parametric equations x equals a plus 3 sine 2t, y equals b cos t, where t is in between 0 and pi over 2, a and b are constants, and O is the fixed origin as shown in figure 2. And that is this summary shown. For part A, we have to determine the value of A and the value of B according to the model. For part A, we know that x equals a plus 3 sine 2t. Now, because we've got a radius of 2, the distance from the y-axis to C is 2, meaning A is equal to 2. And to find out the value of B, we know we have a height of 7, meaning b is 7. So that means x is equal to 2 plus 3 sine 2t, y is equal to 7 cos t. Part B. Using algebraic integration and showing all your working, determine according to the model the volume of the vase, giving your answer to the nearest centimetres cubed. If we take a look at figure 1, we've got the volume of the bottom bit, which is V1, and the volume of the top bit, which is V2. This is a cylinder, and this shape we can find the volume of by using the volume of revolution. We rotate CD about the y-axis, and in doing so we end up with this volume V1. We know for a volume of revolution about the y-axis, that's given by pi times the integral of x squared times dy over dx with respect to t. Now we know what y is, so at this point we can work out what dy over dx is. That is negative 7 sine t. And so we can find out the volume V1. For the volume V1, we've got pi times by the integral of. Now here we have a lower limit of pi over 2 and an upper limit of 0, and that is because going from C to D, y is decreasing. We know what x is, so for x squared we will have 2 plus 3 sine 2t squared multiplied by dy over dx, which is negative 7 sine t. And we integrate this with respect to t. And just to reiterate, for the limits, we are going from pi over 2 to 0 because y is decreasing. So I've got negative 7 pi times the integral from pi over 2 to 0, and the reason we've got this negative 7 is from here. Now 2 plus 3 sine 2t squared, that's 4 plus 12 sine 2t plus 9 sine 2t squared, multiplied by sine t dt. And now we have to multiply the sine t into this bracket. So I've got this negative 7 pi times the integral from e over 2 to 0 of, well, here I'd have 4 sine t plus 12 sine 2t sine t plus 9 sine 2t squared sine t, and we integrate with respect to t. Now what we can do to integrate this is to recognize that sine 2t is equal to 2 sine t cos t. So I've got negative 7 pi times the integral from pi over 2 to 0 of, well, I've got this 4 sine t, that's not going to change, and then I've got 12 sine 2t, which I can rewrite as 2 sine t cos t, and I multiply this by sine t, and then I add on to this 9 sine 2t squared, so I've got 9 times by 2 sine t cos t squared multiplied by the sine t, and I integrate with respect to t. So I've got negative 7 pi times the integral from pi over 2 to 0 of 4 sine t, and here we would have 24 sine t squared cos t, and here we would have 36 sine t cubed cos t squared, and we integrate with respect to t. So I've got negative 7 pi times the integral from pi over 2 to 0 of 4 sine t, and then here I've got the 24 sine t squared cos t, and then I've got 36 times by sine t cubed. The sine t cubed I can rewrite as sine t times sine t squared, and then I've got this cos t squared. So I've got negative 7 pi times the integral from pi over 2 to 0 of 4 sine t, and then I've got 24 sine t squared cos t, and then I've got 36 sine t, and this sine t squared I can rewrite as 1 subtract cos t squared, and then I multiply by cos t squared. And if I expand, I've got negative 7 pi times the integral from pi over 2 to 0 of 4 sine t plus 24 sine t squared cos t plus 36 sine t cos t squared, subtract 36 sine t cos t to the 4 dt. Now, eventually I want to use the reverse chain rule, so we can write this in a more integrable form. I've got negative 7 pi times the integral from pi over 2 to 0, and then I've got this 4 sine t. Now this term here we can rewrite as 24 times sine t squared cos t. This term here I can write as 36 sine t and then cos t squared, and this term here I can write as negative 36 sine t cos t to the 4. The reason for that is because the differential of the bracket is outside of the bracket, and that allows us to use the reverse chain rule. So if I use the reverse chain rule, well, I've got this negative 7 pi. Now if I integrate 4 sine t, I've got negative 4 cos t, and if I integrate 24 sine t squared cos t, well, I add 1 to the power, and then I divide by the new power and divide by the differential of the bracket. And for this term, we add 1 to the power, divide by the new power, and divide by the differential of the bracket. And then for this term, add 1 to the power, divide by the new power, and divide by the differential of the bracket, as we see here, and we evaluate this from pi over 2 to 0. So if we tidy this up, we've got negative 7 pi times pi. Now here I've got negative 4 cos t. For the next term, I've got 8 sine t cubed. For the next term, I've got negative 12 cos t cubed. And for the next term, I've got 36 over 5 cos t to the 5. And I evaluate this from pi over 2 to 0. Now, before we do anything else, the cos of 0 is 1. The sine of 0 is 0, cos of pi over 2 is 0, and the sine of pi over 2 is 1. We will use this when substituting in these limits. So I've got, for my upper limit, negative 7 pi times pi. Here I've got negative 4. Now remember I'm substituting in 0. So I've got negative 4 times cos of 0, which is 1, plus 8 times pi sine of 0 cubed, so that's going to be 0 cubed. Then I've got negative 12 cos t cubed when t is 0, so that's going to be negative 12 times by 1 cubed. And then I've got 36 over 5 times by cos t to the 5 when t is 0, so that's going to be 1 to the 5. And then I subtract from this. Well, I've got this negative 7 pi, and then I've got negative 4 cos t, so that's going to be negative 4 times by 0, plus 8 times by 1 cubed, subtract 12 times by 0 cubed, plus 36 over 5 times 0 to the 5. Now, I've got negative 7 pi, and if I simplify what's in this bracket, I get negative 44 over 5. And then I've got negative 7 pi, which is positive 7 pi. And in this bracket, we end up with 8. So I've got 7 pi multiplied by 88 over 5, which is 588 pi over 5. That's what the volume V1 is. We can now find out what V2 is. v2, that's pi times by 2 squared times 4.5, which is 18 pi. So the total volume will be 588 pi over 5 plus 18 pi. Let's work out this numerical value. I've got 588 pi over 5 plus 18 pi. As a decimal we get 425.99, etc. So we have 426 centimeters cubed. Part C. State a limitation of the model. A limitation of the model is the vase may not be completely smooth.